My name is Tiffany, and I'm going to be presenting today over economics of energy storage deployments. This presentation will have some audio from Murat, and even though we are recording, we do want to express that we are excited over this presentation, and we hope that our excitement is shown. So, today we're going to be talking about a little bit of background information of what energy storage is, a couple of the projects that are happening in the US, as well as how Missouri is connected to that, which is pretty cool. Some barriers to continuing further research into energy deployments and storage projects in general. Then I'm going to have some audio from Murat. He's going to talk about the cost benefit analysis of the storage projects. And then I'm going to wrap it up with some future recommendations and deployments, as well as the conclusion. So, energy storage, what is it? So, storage basically is the ability to capture energy at a certain time and then access it and use it at a later time, which in our case, it's not that simple. We do have some barriers when it comes to technology, costs, that goes along hand in that. Typically, storage is used in performance in terms of lithium ion batteries. So right now, the current projects in the U.S. involve using lithium ion batteries or the recyclable batteries to aid in current grid technology. So basically, they use the stored energy to aid during peak times where other renewable energy forms are used hand in hand along with grid to cover those peak and intermittencies in demand. So right now, Missouri, being the lead producer in lead, um, they currently use part of storage in terms of recycling the lead acid battery. There are facilities that use this technology, and with the use of this technology has increased job employment in recycling and mining. So companies who do use the recycling lead acid battery created jobs, and in turn, it created more so what we consider a circular economy or a small scale version of a circular economy. The use of renewables to in turn create a more sustained economy. So, as I mentioned earlier, there are some barriers. Of course, with storage being a very new and growing technology, there's questions like how much will it cost, who's going to control it. On terms of the utility provider side, there's different type of municipal utilities, and not just municipal utilities, but different types of utility providers in general. Um, who is going to monitor it, how to market it, whether there's going to be incentives. All those questions seem to still be in the process of being answered as the technology grows. And that, with that being said, investing in cost, there's not enough incentives or even investing in general for energy storage technology and projects. And that's because the costs to build the infrastructure needed to operate this type of technology are very high. Investors are trying to understand their um, return on their investment, whether it's going to be great or not so great. With that being so up in air, such high risk, there's not enough investing or cost that goes into that. But that also hinders the growth of the technology at the same time. Without the investments, there's still a lot of questions up in hand as far as the technology being used. So with that being said, that's why the technology there itself is a barrier. Right now, it's only been used for short-term energy projects and not long-term or large-scale projects. So right now, the recycling battery technology, they still have some mandates, I guess, more so to address, which is more so how to store it safely, reduce the costs for maintenance and repairs. In terms of the battery itself, reduce the overall cost to the end user. Like if this is something that we're gonna use, on a per individual basis. We want it to be on a cost that individuals can also afford. So now I'm going to turn it over to Murat's part of the recording to explain the cost benefit analysis.
I'm going to talk about the future of energy storage in terms of cost. And for next decade, what we expect is in Midwest area, a large number of thermal units such as coal, nuclear gas are going to retire. So in order to overcome, most of private companies or public institutions already started to focus on renewables and energy storage. This is the table from the article Energy Transformation and Energy Storage in Midwest and Beyond. As this table represents, according to data from Global Energy Storage Database, US Department of Energy, future planned battery projects capacity is 508 megawatts in total. These projects indicate that Minnesota and Wisconsin states' strategy for battery storage investment will allow low-cost energy production and reduce the need for non-renewable technology. By the way, this graph represents only battery projects which are their capacities bigger than 1 megawatt. As we all can see, the planet capacity of battery storage is 580 megawatt. Depending on this data, in this part of the paper, I'm going to try to make a comparison to understand benefits of battery storage or energy storage, comparing with other type of energy facilities for the same amount of capacity. Total cost represent the sum of capital cost, power conversion system, balance of plant, construction and commissioning, operation and maintenance fixed, and operation and maintenance variable. Here, capital cost covers different components that vary by technology type. For pumped storage hydropower facilities, it includes waterways, reservoirs, pumps, and electrical generators. For compressed air energy storage systems, it includes caverns, compressors, and generators. For batteries and capacitors, capital costs pertain to the procurement of the direct current energy storage unit. For electrochemical storage units, the capital cost reported within this report includes electrodes, electrolytes, and separators, etc. Power conversion system includes the cost for the inverter and packaging, as well as container and inverter controls. The balance of plant typically includes the components such as site wiring, interconnecting transformers, and other additional ancillary equipment. Here, construction and commissioning costs, also referred to as engineering, procurement, and construction costs, consist of site design costs, costs related to equipment procurement, transportation, and the cost of labor parts for installation. Fixed operation maintenance includes all costs necessary to keep the storage system operational throughout the duration of its economic life that do not fluctuate based on energy usage. Variable operation maintenance includes all costs necessary to operate the storage system throughout the duration of its economic life, and is normalized with respect to the annual discharge energy throughout. This is a summary of compiled 2025 predictions for cost and parameter range by technology type for bulk energy storage systems. Here I had to let you know about a couple of stuff important. In most of the papers I read, energy to power ratio is assumed as 4 for the battery storage systems. That's why dollar per kilowatt hour values are obtained by the multiplying dollar per kilowatt with 4. Also, energy to power ratio is assumed as 16 for pumped storage hydropower and compressed air energy storage facilities. As well, this table is a summary of compiled 2018 findings for cost and parameter by technology type for non-bulk energy storage systems. So depending on all those informations, I made a calculation for 580 megawatt capacity. Because as I mentioned in the beginning of the paper, for next decade, this is the capacity for plant battery storage systems. Here the calculation made for 4 years operation time. As a result of my calculations, lithium-ion battery and solar panels are leader in terms of cost. Assuming compressed air energy storage and systems and combustion turbine systems are not the most common way to store or produce the energy, lithium-ion batteries will be the future of energy storage systems in terms of cost and performance. Also taking into consideration that the Missouri state is the leader of lead mining in the United States, Missouri state can use this as an advantage since lead acid batteries are the second best choice in terms of cost, depending on my table.
So, as you guys have heard from Murat, um, the solar connected with energy storage seems to be a viable solution to combat overall storage concerns as far as a typical project to encourage investors to invest in. Um, with that being said, a way to overcome the barriers in terms of public policy could be to develop just small PPAs, which are purchase power agreements. These are contracts in which the property owner or third party developer or whoever it is that's going to install the technology agrees to purchase enough to fill a device at a set price in which you can use to access it for your electricity. Typically, the price is set lower than the retail price to incentivize the purchase of a cheaper electricity plan. There are issues that arise with that, of course, because the energy is sold based on market competition, and the incentives sometimes don't go hand in hand with the costs, and it could cause higher costs on the utility provider or on the customer's end, depending on how the utility provider and customer's contract is set up. So I feel like with further research into renewable energy and more investing into projects such as these, we could do more feasibility studies to back small PPA agreements to overall turn into some form of public policy and mandates to help affect and control and monitor storage as it grows and develops and as it becomes a technology that we may use. So, in conclusion, energy storage is being able to store energy and access it at a later time. Missouri is keen on energy storage due to the lead acid battery recycling and the technology that we use as a lead producer in lead. Some current barriers in storage involve the cost of the capital inside as well as the customer's end, limitations to define monetized of storage, public policy, and undefined responsibilities for distribution, as well as technological challenges for storing and collecting. Some future developments that we hope to aim to overcome these barriers include reducing the cost to manufacture the necessary parts, maybe creating contracts and strategies for monitoring, encouraging customers to use this technology and using that to build data, create feasibility studies to encourage investors and investing more capital gains into energy storage. Overall, we feel like more research can be done and developed into energy storage combined with solar energy to see if it can reduce costs to the end user. The use of purchase power agreements, PPAs, and clean energy programs can help incentivize and use more and create more usage of energy storage technology, as well as adopt storage in general. And overall, we just hope that this presentation served as a useful resource to encourage more investing in energy storage projects, deployments, through this evidence that we've presented here today. These are our references. Thank you so much. Thank you, MEI, for hearing us and being on the line today. Thank you, Dr. Canfield, for giving us the opportunity to present on this topic. Murat thanks everyone, even though he's not able to say that in his own recording. So, on behalf of him and I, we thank you all, and we hope everyone has a great rest of the semester.